Hello everyone. In this lecture, I shall discuss the improper integral of second kind. Recalling my past lecture on improper integral of first kind, where I have discussed the background of the improper integral. As I have told you, once the limit of the integration is infinity or the integral is unbounded, then it is a category of the improper integral, and it is divided into three categories: first kind, second kind, and third kind. So you see the three integrals here, they almost look alike, okay, but you see this first integral here, it is of first kind. It is of first kind. It is of first kind. Why it is of first kind? Because of the presence of the infinite limit here. In the second integral, you see the function is discontinuous at 0. At 0, it is discontinuous, right? It is discontinuous. So what will happen? It is a second kind integral. It is a second kind integral. Second kind integral. Now we can resolve this third kind of integral. This integral will be equal to here integral 0 to 1 dx by x square plus integral 1 to infinity dx by x square. You see now. So now this integral, it is your second kind. It is your second kind because discontinuous at 0, and it is of your first kind. It is of your first kind. It is first kind because of the presence of the infinity here. Right? What can you say about the convergence of this integral? With this previous knowledge, this integral here by the p test, here p is 2. This power p is 2 here. So this p is 2. If it is greater than 1, then it is convergent. Okay, then it is convergent. But here you see p is 2 here, right? P is 2 here, it is greater than 1, right? Here it is for second kind, right? It is almost in the opposite way of the test. You see here, so here this integral is divergent, right? This integral is divergent here. I will tell the details. This integral is divergent. I will tell you the details. This is divergent. In short, I am writing dgt. Right, this is divergent. Now what happens to the third integral? As I have told you, this is divergent here. Right, this is divergent here, and this is convergent here. Right, dx by x square. This is convergent here. So now divergent plus convergent is here divergent here. So this integral is divergent here. Okay. So these three similar looking integrals, but you see the nature of the integral. The first one is convergent and it is of first kind. The second one is divergent and it is of second kind. And third one is a third kind and it is the combination of first and second kind, and it is also divergent. So let me to tell you now the different way of testing the convergence and divergence of the integral. Now before discussing the details of the integral of second kind, let me to introduce myself. I am Professor Sushant Kumar Paikray, currently working as a professor in the Department of Mathematics, Veer Surendra Sai University of Technology, Burla, Odisha, India. So now let us see the second kind of improper integral and what is the way of evaluating the direct integral, and there are different aspects of the test of convergence. So without much delay, let us now start our integral. Now coming to the definition, an integral of the form a to b fx dx where both a and b are finite, but fx is discontinuous. At one or more points. Okay, one or more points. It may be at 1 point or more than 1 point. Means you can say you may have at a the discontinuity at a, or the discontinuity at b, or the discontinuity at both a and b, or the discontinuity at c, where c is a point here. C is suppose something, it lies between a and b, right? And it may be more than also two intermediate points, right? Accordingly, we'll see the cases of evaluation. Now let us evaluate the improper integral by considering some specific example. Suppose I am considering one example, integral 0 to 1 dx by root x. Okay, so this integral, here you see it is discontinuous at at 0, right? Means fx here is 1 by root x, fx is 1 by root x, here is discontinuous at 0, is not it? So how you will evaluate it? If we want to directly evaluate this integral, it will be the integration of 1 by root x is 2 root over of x with the limit 0 to 1, okay. So this will be 2 into 1 minus 0 is my 2. But since there is a discontinuity here, rather than directly evaluating like this, the correct approach is we just avoid this discontinuity. This integral will be equal to some limit epsilon tends to 0, okay. This is epsilon to 1 dx by root x. So now this discontinuity is removed by this epsilon. So for the students of higher mathematics, they should adopt this procedure. So this is equal to the limit epsilon tends to 0, 1 by root x, integral is 2 root x, and the limit is here epsilon and 1 here. So this will be limit epsilon tends to 0, it is 2 into 1 minus 2 into root over of epsilon. Now it is here 0, epsilon 0 means it is here 0. So this is here 2 here, okay. So this is actually the correct approach for the students of higher mathematics, okay. So now you see, suppose let me to tell you another example. Suppose integral 0 to 1 dx divided by 1 minus x root over. So you see here the discontinuity at 1 here, right? So how you will write it? You will write it limit some epsilon tends to 0, here integral 0 to 1 minus epsilon, okay, 1 minus epsilon. So here if discontinuity at the lower limit, you should write it is lower limit plus epsilon, right? If the discontinuity at upper limit, you should write it upper limit minus epsilon. It is 1 by 1 minus x root over dx, and you must be knowing the integral x to the power n, integral is x to the power n plus 1 by n plus 1. This is the integral, okay. So if I evaluate it and there is a minus sign here, so it will be minus twice root over of 1 minus x, okay. And with this limit of integration is epsilon to here 0 to here 1 minus epsilon here, and limit epsilon tends to 0. Now we just evaluate it. So now if you simplify it, upper limit you substitute and lower limit you substitute. So this is minus, now this will be here 0. So because of epsilon is 0, so now this 1 and minus 1 and cancelled. So this is minus of minus 2 is 2 here, okay. Or if you like, you can directly evaluate it, integral 0 to 1 dx by 1 minus x root over. So this will be here minus of 2 root over of 1 minus x, and the limit is from 0 to 1, okay. And we may proceed like this, but this should be the correct approach because the discontinuity at 1 here and 1 is included. That's why the proper approach is like this, okay. Now suppose the discontinuity at the end point. Suppose coming to another question. So here you see the discontinuity at both 0 and 3, right? It is discontinuity at both 0 and 3. So how to overcome it? So you will write it, you will take some intermediate point here. It will be some say 0 to some a and plus say some a to some 3, or you may take some specific a here. Now it is here dx by x into 3 minus x, and it is here dx by x into 3 minus x, okay. So now we remove it, the discontinuity. So since the problem is here, we write some limit epsilon 1 tends to 0, it is integral 0 plus epsilon 1 to a dx by x into 3 minus x. And here the problem is at 3, so we take limit some epsilon 2 tends to 0, integral a to 3 minus epsilon 2 dx by x into 3 minus x. Okay, and we should continue to simplify it. We apply the partial fraction here and we will solve it. We apply the partial fraction and we solve it. Okay, now let us see another integral where we find the discontinuity at the intermediate points. You see this integral here. If you factorize the denominator, it is 0 to 3 dx divided by x minus 1 into x minus 2, middle term factorization. So now you see, so this discontinuity at 3 here, discontinuity at 2 here, and this 1 and 2 are within 0 to 3, yes or no? So it is discontinuous at 1 and 3, and which are both are within this limit of integration. Okay, so how to split it? So we will split it. So this integral will be equal to here 0 to 1. Now 1 is a discontinuity here. Then we have 1 to some another point. Let you take it some 3 by 2, 1 to 1.5. Then you take some 1.5 means 3 by 2 to 2 here, right? Then you take here 2 to 3, right? So now here it is, I am taking my f is 1 by x minus 1 into x minus 2. So it is my f. So here the discontinuity at 1 here, so I should write it 1 minus, right? 1 minus, and here the discontinuity at 1 here, so I write it 1 plus because it is in the lower limit. And here the discontinuity at 2, I write it 2 minus. Here the discontinuity at 2, so I write it 2 plus. In that way f dx, in that way I can write this is f dx, or as usual in the previous process, it is my limit of epsilon 1 tends to 0, it is 0 to 1 minus epsilon 1 f dx, plus for this integral we have limit epsilon 2 tends to 0, it is my 1 plus epsilon 2 to some 3 by 2, or any value we can take in between. So this is my f dx. Then for my third, so this is my limit epsilon 3 tends to 0, integral 3 by 2 to 2 minus epsilon 2 f dx, and plus my limit some epsilon 4 tends to 0, integral here 2 plus epsilon 4 to 3 f dx, and we will evaluate it accordingly. Okay, so this is the direct way of evaluation. Now what happened if the integral is complicated and quite lengthy to evaluate, okay, and it is difficult, and only the convergence is asked, whether it is convergence or not. So then without having much calculation, within one line we can say what will be the answer, and for which we need the test of convergence. So what we need test of convergence. If we recall, if our type 1 where we have seen the p-test, likewise here we have our p-test. What is p-test? Right? What is p-test? For improper integral of second kind. If you recall the first kind, then integral a to infinity dx by x to the power p converges if p greater than 1, right, and diverges if p less than is equal to 1. So this is the thing, it is already known in first kind. Now what will happen here for second kind, right? What will happen here for second kind? For the second kind, here integral dx by, suppose we have the discontinuity at a here, means we can avoid it by taking a plus epsilon. So dx by x minus a to the power p, and some b is here. Then this integral is convergent if, you see here it is opposite to this, okay, if p here less than 1 here, right, and divergent p less than 1, and divergent when? Divergent if p greater than is equal to 1. You see, so here the discontinuity at a here, right? Discontinuity at the lower limit, discontinuous at a lower limit, then we can have this. Now if the discontinuity at b here, right, likewise if you have the discontinuity at b here, so I write it b minus, okay. So dx by, just for a notational sake I am writing as it is my b minus x to the power p, it is my b minus x to the power p is convergent. Likewise the same thing, if p less than 1, and is divergent if p greater than equal to 1, okay. So this thing is same, but here the approach is, if it is discontinuous at the lower limit, then we have like this. If it is at upper limit, then we have like this. Here it is discontinuity at b. So it can be removed by taking b minus epsilon, right? So now this is the case, and just this is the contrast to this, but the method is similar, but only you see here at the value of the p, it is somehow opposite. So this is for your second kind. For second kind we have, this is the test, okay. For second kind we have, this is the test. Now we implement this test here, right? We have solved here example 1 and example 2 here we have solved. Now let us see what will happen to example 1. If you implement this test here, the discontinuity at 0 here. Now the power is what? The power of x is what here? So it is dx by x to the power half here, is not it? 0 to 1. So that means I can write it 0 to 1 dx by x minus 0 to the power half. So what is my p now? My p is half here, is less than 1. Once it is less than 1, then it is convergent. So without evaluating it, now the evaluation will give you this sum, but it is not always easy to evaluate. Sometimes it is asked just to test the convergence. Then this p test will give you, this is because of the p test, right? Clear? So here you should note that this a should be some positive, right? This a should be some positive, okay. So if I ask you one integral 1 to infinity dx by x square, as I have told you at the beginning, okay. So here a is 1 which is greater than 0. Now it is p is equal to 2 here which is greater than 1, right? P is equal to 2 greater than 1, that's why it is convergent. And as I have told you here, if I ask you some integral 0 to 1 here dx by, suppose my 1 minus x, right? You see here, so here the discontinuity at 1 here, so we should go for this test, right? We should go for this test. It is b minus x, so now it is my, what is p here? My p is equal to your half, is my less than 1, right? So once it is less than 1, means it is convergent, okay. So already we did it here, isn't it? We did it here. We see by evaluating directly we are getting this sum, but if we are getting a finite sum, then it is convergent, and here it is convergent. If only test is asked whether it is convergent or not, then this is enough. This is my convergent. Suppose coming to one more example, it is suppose asked minus 1 to 1 dx by x to the power 2 by 3. Here you see, so the discontinuity at 0, the discontinuous at 0, but 0 is here in minus 1 1, it is in between here, so we have to split it here. It is integral minus 1 to 0 dx by x minus 0 to the power 2 by 3 plus integral 0 to 1 dx by here x to the power 2 by 3. We can likewise we can write it my 0 x minus 0 to the power 2 by 3, and here the thing is that you see the discontinuity at 0 here, right? So it is my, you see, so the discontinuity at the upper limit here, so it should be b minus x, it should be 0 minus x, but you see here the limit is positive a to b, Now here it is negative, right? So if I substitute my put my x is equal to minus y, then this limit will be converted to here 0 to 1. In that way it will be converted, isn't it? So that's why, so this p here is here 2 by 3, p here is 2 by 3, and here the discontinuity at here means it is 0 plus I can write, right? So now the discontinuity is here, and it will be also p is equal to here 2 by 3. This is less than 1 and this is also less than 1, right? This is convergent and this is also convergent, okay? So therefore convergent plus convergent, and the final answer is convergent. Therefore this integral is convergent. So this integral is convergent. Now in view of this, if I want to write in details, it will be your what? Dy by y minus 0 to the power 2 by 3. Now the discontinuity at 0 here, okay? So in that way, if the negative limit is there, you can apply the formula in that way, clear? So now coming to another important test, that is your mu test. Now let us discuss the mu test. It is again a powerful test. Let me to remind you here the improper integral of first kind, okay? Then this comparison will help you to avoid the confusion, so that the implementation will better. So if I recall this, let mu be a real number if mu greater than 1, right? You see, mu greater than 1, for which x to the power mu into f of x, limit x tends to infinity is equal to a. This a is a finite value, means exist, finite, right? It may 0 or may not 0, we don't bother about this, but it is a finite value, what we bother. Then what will happen? Then your integral a to infinity f dx is convergent, okay? Likewise, so here it is convergent. Likewise, if mu less than is equal to 1, such that, or for which your limit x tends to infinity, x to the power mu into fx is equal to a, right? And this a here is should not equal to 0, right? A is a finite value, but not equal to 0, but non-zero. You see here, there is no restriction. It may 0, it may non-zero for mu greater than 1. But here, you note it, mu, this a should be non-zero, right? Or plus or minus infinity, whatever it may be. If anything, it may be finite value other than 0, or it is plus or minus infinity, then your integral a to infinity f dx is divergent, okay? You see, it is divergent. This is mu less than equal to 1, and this limit is a finite value other than 0, or it is plus minus infinity. What will happen if a equal to 0 here? If a equal to 0 here, then this second test fails here, right? This test fails here, right? This for only the second one, for mu less than equal to 0. Here there is no restriction, clear? Now how this mu will be taken? Note, here mu is the difference of highest power of x in denominator minus highest power of x in numerator. In that way you can take it, right? Now in view of this, let me to write for our second kind. For our second kind, right, let there exist a number mu, right? Mu, and mu here is less than 1. I have told you the reverse of this, okay? Here mu greater than 1 here, and mu less than 1, and one more restriction, and mu such that here I am writing 0 less than mu less than 1, okay? 0 less than mu. One more restriction I have included here. 0 less than mu less than 1 means mu less than 1 here. If there is a number mu such that, right, limit x tends to a, x tends to a, x minus a to the power mu into f of x, right, is equal to a. It has to be finite. Finite, 0 or non-zero, 0 or non-zero, no restriction, 0 or non-zero, non-zero, anything, any finite value, right? Then any value, any finite value I say, any finite value, to be more specific, any to more general, any finite value. Then the integral dx by x minus a, the integral, actually the integral fx, okay, the integral fx dx is convergent, here. It should be a plus 2b, right, discontinuity at a here, and it should be here a plus, right. Likewise, if it is for discontinuity at b, then what will happen, right? If it is limit x tends to b minus, it is b minus a to the power mu, right, fx is equal to a, finite, any finite value. Then your integral a to b minus f dx is convergent, okay, is convergent. Here what is the value of mu here? This is the same here, mu is less than 1, right, and to be more specific, mu lies in between 0 and 1, right, and then in this case it is convergent. If you compare this with here, right, when mu greater than 1, then it is convergent. Clear? Now likewise, what will happen if your mu greater than equal to 1? Likewise, for mu greater than is equal to 1, okay, limit x tends to a plus x minus a to the power mu fx is a here is finite and non-zero and not equal to 0, or plus and minus infinity, then integral a to b f dx, here the discontinuity at the lower point, dx is divergent, okay, is divergent. And similarly, if the discontinuity at b, limit x tends to b minus, okay, it is b minus x to the power mu fx is a, finite and not equal to 0, or plus or minus infinity, okay, then here a plus, then here a to b minus f dx is divergent, okay, is divergent. Clear? Now if in the second case, here only if a is equal to 0 here, and it is for mu greater than equal to 1 case, right, then test fails, then your test fails here, okay. So you should compare these two tests here. It is almost similar. Here for your first kind, your mu is less than equal to 1, right, and here a is finite and non-zero, then it is divergent. Likewise here mu greater than equal to 1, right. So now let us implement this to some examples. So now let us apply mu test to these examples. In fact, these are the examples we have already solved it directly, and by p test also we have did it. Here p is equal to half, less than 1, convergent we did it. Here p is equal to here half, okay. Now here discontinuity at 1, 1 minus, and discontinuity at 0, 0 plus, okay. So now this is also convergent. We have seen it directly by p test. Now we add up the mu test. What will happen by my mu test here? So the power in the denominator is x to the power half. In the numerator the power is 0. So here mu is my half minus 0 is equal to my half, right? So mu is equal to my half. So what will happen here? Limit x tends to 0 plus, right? Here mu x minus 0 to the power half into fx. Into fx is my 1 by root x, right? 1 by root x. So this cancelled is equal to my 1 here. So this 1 is a finite value here. Finite value here. I am telling that mu is less than 1 here. For less than 1. And in fact 0 less than mu less than 1. Is not it? So here what will happen? So this is convergent here. This is convergent here by mu test. Right? For your mu test, you see, for your mu test 0 less than mu less than 1. And this is a finite value. No restriction of 0 or non-zero. Now what will happen likewise here? Likewise here we have the discontinuity at B here, upper point here. So here in this case here limit x tends to 1 minus here. Okay, here 1 minus x to the power mu is my half, right? Mu I am taking mu here. Mu is my half. This p by previous way. Here I am taking what is mu here. My mu here is denominator power of x is half, numerator 0 is my half here. So this is my this into fx. What is fx? Fx is here 1 by 1 minus x root over. So this and this cancelled here. This is equal to 1. This is finite value. No restriction here. Finite value. So what will happen? This is convergent. So the same problem can be solved by your mu test, by p test also. The same problem can also be solved by using your mu test. Now let us solve some more examples. Suppose you have one more question. Test the convergence of this integral. You see here. So here the discontinuity, put the denominator equal to 0. So x is 0 and 1. So 0 and 1 are included within the range here. Okay. So here discontinuous at 0 and 1. So we have to split this integral. So this integral, let it be my I. So my I integral will be 0 to 1 dx by x into 1 minus x root over plus integral here 0 to 1 dx by x into root over of 1 minus x. So I split it to understand here. So here you take some intermediate point between 0 and 1. Let it be my some point A. Some point 0 to A and my A to 1. This A to be specific I may take half. Any value to be specific I may take it half. No issue here. Or in general you take A. If you are taking A, so A is something, some point in between 0 and 1. Right? Or to be more specific I write a particular value here. So that is equal to, suppose I am writing now the discontinuity at 0 here. So now I am writing 0 plus here. Now the discontinuity at 1 here, I am writing 1 minus here. So what is my mu in this case? My mu in this case will be in the sense of 0. In the sense of 0. So mu in sense of 0. Sense of 0 is my what? So this is power of x here is half. So this is half, numerator no, power is 0. So it is my half. So now what happens to my mu here? So my mu in sense of 1 here, right? So now what is this is my x is here, okay, root x also. So now in the sense of this, what is the power of x here? Is my half here, half and minus 0 is my half here. Okay, now you see, so this is my, suppose my I1 and suppose my I2. Now what happens to my I1? Now for my I1, it is my limit x tends to 0, right? Here mu is less than 1, mu is equal to half is my less than 1, limit x tends to 0 plus. Okay, so it is my x minus 0 to the power half into fx is my 1 by x into 1 minus x root over. Now this cancelled. Now putting x is equal to 0, this is my 1, it is finite. We don't bother about 0 or non-zero because mu is less than 1. So this integral is my convergent. Now what will happen to my second integral? What will happen to my second integral also? For my I2 here, it is my limit x tends to 1 minus, because it is at the upper limit, it is my 1 minus x to the power half, okay, into fx is 1 by root x into root over of 1 minus x. This and this cancel now. So now putting x is equal to 1 here, it is 1, right? It is finite. So the second integral is also convergent here, is not it? So this integral converges, and this integral is also converges. Therefore, this what happens to I is I1 plus I2. It is converges plus converges. So this is my convergent here, okay? This is my convergent. So this integral I is convergent. Let me to solve you one more example for mu greater than 1. Suppose I am considering one more example. The integral is given. My I is equal to this. So here you see it is, if the denominator is equal to 0, then I am finding discontinuity at x is equal to 0 and 1. So 0 and 1 are the both endpoints here. So we have to split the integral. So my integral I will be 0 within 0 and 1, some intermediate value. Suppose I am taking half or any value. It is my dx by x into root over of 1 minus x. Plus I am taking my half to 1 dx by x into root over of 1 minus x. Since the discontinuity is here at 1, I write 1 minus, and discontinuity at 0 here, I write it 0 plus. Now here in the sense of 0, what is my mu here? The power of x is 1 in the denominator, the power of x is 0, it is my 1 here. So this first case here is, the first case here is mu is here greater than equal to 1 case here, okay. Now limit x tends to here 0 plus, okay, it is my x minus 0 to the power mu is my 1 here into here fx is my 1 by x into root over of 1 minus x. So this cancelled here, putting x is equal to 0, this is my 1, a finite value here, and which is finite and not equal to 0. You see, for greater than 1 we need finite and not equal to 0, okay. So therefore this integral is divergent. So this is my I1 here, this is my I1, and this is my I2. So therefore my I1 is divergent. Now what happens to my I2 here? So now I have to see the mu in the sense of 1 here. So what is my mu here? So mu is, the power is here 1, denominator, and numerator the power is 0, it is here 1. So my limit x tends to my 1, limit x tends to 1 plus, okay, because the discontinuity at the 1 minus, upper limit. So it is my 1 minus x to the power mu is 1, my fx is 1 by, in the sense of this 1, this power here is, the power here is half, okay, power here is half. So this is here 1 minus x to the power, this is my half, and x is here. So this and this cancelled. Now 1 by 1 is 1 here, Now here I am examining the case of mu is less than 1, is not it? I am examining the case mu less than 1 here, this case. So here I need a, it is a finite value. We don't bother about 0 or non-zero. So now it is here convergent here. So this implies my I2 is convergent. Now what happens to I1 plus I2? Therefore I is equal to I1 plus I2 is divergent, okay? Is divergent, because divergent plus convergent, right, is divergent here. So this question is divergent here. You see, this example and this example are looking similar, but you see here it is divergent. So be careful in testing the convergency of the integral. Now let me to tell you, the last test is the comparison test. Now likewise the first kind, it is same. So now here you are given we are given a function f here, okay. You are given a function f here. We compare this function with g. So how will compare it? Suppose you are given a function fx, right? Suppose you have a known function gx. Suppose I have a known function my gx, right? And my given function is smaller than that. Now what will happen here? Now if my gx will converge, gx, the integral gx converges, then fx converges, then integral fx converges, right? Then the integral fx converges. Means, and here I should write a positive term sequence here, right? So that means smaller than a convergent sequence is convergent, right? That means smaller than convergent sequence is convergent, okay, right? Now likewise, if what will happen, I have a larger function. If fx is my greater than gx, my fx is my greater than gx, right? And this larger function is my, if this larger function is divergent, right? This now this fx is the larger function. If the smaller function is divergent, then the larger function fx, integral fx, is divergent, okay? So I can write larger than divergent sequence, divergent integral, okay, is divergent, right? Is divergent. Now what will happen in between? Suppose this is my given function. This is my known function. Right? This is my known function. So now suppose this integral is my, integral h is my convergent, and suppose my integral g is my divergent, right? Then it is larger than convergent but smaller than divergent, right? But here we cannot have any conclusion, integral f, so no conclusion, we cannot conclude anything. Means larger than convergent but smaller than divergent, right? Divergent, no conclusion. Or alternatively we are given fx and we select another gx, we find the limit extends to a minus if the discontinuity at a plus, discontinuity at the lower limit, discontinuity at lower limit a, right? Or this is suppose my limit extends to my b minus fx by gx, if discontinuity at upper limit b, then we will take it like this. Now suppose this integral is my L, a finite value, right? This integral is my L. If L is finite, if my L is not equal to 0 and finite, then both f and g behave alike. What does it mean? That means f and g together converge or diverge, right? Together converge or diverge. Means whenever f converges, g converges. Whenever g converges, whenever f diverges, g also diverges. Okay. Now the moment if L is equal to 0, we just bother about this only. Now if some special case, if L is equal to 0 and integral g converges, then integral f converges, right? And another special case, if L infinity and integral g diverges, then here integral f diverges, okay? So now let us solve some examples to understand these ideas. Suppose you are asked one example, test the convergence of integral 0 to 1 dx by x square into 1 plus x square, okay? So let my f solution, so originally what is given is my f, so 1 by this is my f, let f is equal to 1 by x square into 1 plus x square. So this is given So let I take g. Some g is equal to my, I am taking suppose 1 by x square. I am taking suppose 1 by x square. So that this x square will cancel, in that way I will take. Okay. Now what will happen? What will happen? Limit x tends to 0. Because limit, we are observing the discontinuity at 0 here. Okay. So lower limit. Now it is limit x tends to 0, fx by gx. Fx by gx is equal to 1 by x square into 1 plus x square into x square, and limit x tends to 0. To be more specific, since it is at the lower limit, I am writing 0 plus. Now this x square cancel. Now what is the limit? 1 by 1 plus 0 is my 1. 1. It is not equal to 0 and finite, not equal to 0 and finite, right? So therefore f and g behave alike. But what happens to my g? Integral g dx, right? Integral g from 0 to 1, okay, is my is what? Integral 0 to 1 dx by x square, right? X square. So here, what is the value of p here? So now my p is equal to my 2 here, which is greater than 1. Okay, in this case, p is greater than 1 means it is divergent. So therefore integral g dx is divergent. Once this is divergent, what does it mean? My integral f is divergent, isn't it? Divergent, because of by comparison test. By comparison test. So therefore integral 0 to 1 here dx by x square into 1 plus x square is divergent. Let me to solve one more example. So let me to solve one more example. Suppose this is the integral we are given. Now you see, putting the denominator is equal to 0. The discontinuity at 0 and 1, right? So at both. So we have to split the integral, right? Let my I is equal to, this is the solution, I is equal to 0 to some intermediate value I am taking. To be specific, I write half, or any value you write. 0 to half, it is dx by root x into 1 minus x to the power 1 by 3 plus integral half to 1 dx by root x into 1 minus x to the power 1 by 3. So now here we have the discontinuity in the sense of I am writing 0 plus here. Okay. So now let my gx, so this is my f, let my gx is equal to 1 by root x. If I am taking 1 by root x, then this f by g will cancel. So what will happen? Limit x tends to 0 plus fx by gx, okay, is limit x tends to 0 plus, it is 1 by 1 minus x to the power 1 by 3. It will cancel into root x into root x. This will cancel here, is not it? So this is equal to, putting x is equal to 0, it is my 1 here, right, which is not equal to 0 and finite, right? So therefore f and g behave alike. So but convergence, but integral 0 to 1 gx is convergent. Therefore integral 0 to 1 dx by here root x into 1 minus x to the power 1 by 3 is convergent. My I1 is convergent. This is my I1 say, and this is my I2. Next for my I2. For I2 here integral half to 1 dx by root x into 1 minus x to the power 1 by 3. Now we have to take, this is my f, is not it? This is my f. What is my g? So let my g will be, so now in the sense of this, so now here it is 1 minus. So in the sense of this, I have to think this, okay, g by 1 minus x to the power 1 by 3. So my limit x tends to 1 minus f by g. So this and this cancelled. Okay, so this is equal to limit x tends to 1 minus 1 by root x here is my 1, not equal to 0 and finite value. Okay, so therefore what I am getting, so therefore f and g, integral f and integral g behave alike. But what will happen to this integral? Right, it is here p is 1 by 3 less than 1 here, is not it? Here p is here 1 by 3 is less than 1 here. Clear? So but what will happen here? But integral g dx is convergent as p is equal to 1 by 3 less than 1, right? Therefore by comparison test integral f is convergent. So that means my I2 is convergent. I2 is convergent. So therefore my I is equal to I1 plus I2 is convergent. So here in the same problem you can also apply mu test also. So here in the sense of this you may take here mu is equal to half, here you can take, right? And the sense of this, in the sense of 1 you can take this mu here, mu is 1 by 3 here, okay? Mu is 1 by 3. In both the case it is less than 1, and it will find this will both will converge and converge, okay? So in that way you can alternatively you can also apply the mu test. So p test and mu test can be applied simultaneously to many problems, okay? So this is all about the improper integral of the second kind, right? Now in my upcoming lecture I will tell you the convergence of, in my upcoming lecture we will discuss the convergence of beta and gamma functions, okay? These are also the improper integral. This is most important for students of higher mathematics. So in the upcoming lecture we will discuss the convergence of beta and gamma functions. The video is going to lengthy, so we should close it. Before closing, my request to all of you, if you find this lecture is useful and interesting, please subscribe to this channel, which will boost my motivation to prepare further videos for your benefits. Okay. With this we should close this lecture here. So thank you all. Have a good day.